Good morning, SYBSc students. Today we study special cases of damped oscillations. Okay. Now in last lecture we have obtained the resultant equation of motion and it has the format x equal to a1 e raised to minus rt of r upon twice m plus root r square upon 4m square minus k by m into t plus a2 e raised to minus r upon twice m minus root r square upon 4m square minus k by m. So this is the resultant equation of motion. That means it is the solution of differential equation of damped oscillation. Okay. Now next we consider the special cases. There are three special cases. Hence, first we study first case, that is damping force greater than restoring force. Here in this equation, r square upon 4m square is the damping force because here r is the damping coefficient. Okay, and this k is the restoring force coefficient. Okay, so in first case we have to study damping force is greater than restoring force. That is we write here r square upon 4m square greater than k by m or r square greater than 4mk. Okay, when we consider this case in which r square upon 4m square is greater than k by m, then both exponential term, that is minus r upon twice m plus root r square upon 4m square minus k by m and minus r upon twice m minus root r square upon 4m square minus k by m are negative. That means for this case the both exponential terms, this one and this one, are negative, and when these terms are negative, that means oscillator comes to the rest position after long time. That means in this case oscillator comes to the equilibrium position after longer time without undergoing oscillatory motion. Okay, that means oscillator does not obey oscillatory motion, but it comes to the rest position or equilibrium position after longer time. When we plot the graph of displacement versus time, then the nature of curve is like this. That means here the amplitude decreases exponentially with time, and in this case oscillator comes to the equilibrium position after longer time as shown by this curve. Such type of motion is called as the overdamped motion. Here such type of motion or this type of motion is called as the overdamped motion, right? That means in first case when we consider r square upon 4m square greater than k by m, in this case the both exponential term are negative. That means amplitude decreases with time, right? So in this case oscillator comes to the equilibrium position after longer time without undergoing oscillatory motion. So this curve shows the overdamped motion of the oscillator or case first. Okay, then we consider case second. In case second, we have to consider both forces are equal. That means damping force is equal to restoring force. Okay, equal to restoring force, right? Now for this we write here is r square upon 4m square equal to k by m, or in other words we write r square equal to 4mk. Okay, now when we consider this case r square upon 4m square equal to k by m, then this equation becomes x equal to a1 e raised to minus rt upon twice m, because here r square upon 4 m square equal to k by m. Okay, then we get a1 e raised to minus rt upon twice m plus a2 e raised to minus rt upon twice m. Okay, so next we write here x equal to, we take common e raised to minus rt upon twice m, so right here e raised to minus rt upon twice m in bracket a1 plus a2. So we put a1 plus a2 as a a, then we get this equation as k e raised to minus rt upon twice m. Now this equation contains only one constant, that is a. So this cannot be a proper solution of differential equation. Okay, so in order to obtain proper solution, we have to substitute the term, that is r square upon 4 m square minus k by m equal to, say, small r. Therefore we putting root r square upon 4 m square minus k by m equal to, say, small r. Now here this r is very small. When we put this value root r square upon 4 m square minus k by m equal to r, then this equation reduces to right here, that is x equal to a1 e raised to minus rt upon twice m plus rt, okay, plus a2 e raised to minus rt upon twice m minus rt, right? Then in next step, right here, by taking e raised to minus rt upon twice m common, therefore x equal to e raised to minus rt upon twice m to take common. Then we have to write this a1 rt, okay, a1 rt plus a2 minus rt, like this. Okay, then we take a1 plus a2 common, therefore x equal to e raised to minus rt upon twice m, then we take common here, that is a1 plus a2, in first bracket we write a1 plus a2, and in second bracket we write, that is plus, right here in next term we write here this okay, here we have to write this e raised to rt, okay, right here e raised to rt, here we write e raised to minus rt, okay, right? So right here x equal to e raised to minus rt upon twice m, we take common a1 plus a2 in first, and in next bracket we take e raised to rt plus e raised to minus rt. Okay, now in next step we have to write the equation right here. Before taking common, we write this equation, that is x equal to e raised to minus rt upon twice m, in bracket we write a1 e raised to rt plus a2 e raised to minus rt again. Okay, then we have to write this equation as x equal to e raised to minus rt upon twice m, okay, in bracket we write a1, right? Then e raised to rt, we write the expansion of this e raised to rt, only first two terms, that is 1 plus rt plus so on, plus A2 in bracket 1 minus RT plus so on like this, and is the expansion of e raised to RT and e raised to minus RT only in two terms like this. Then we take common, that means A1 plus A2. In next step we write x equal to e raised to minus RT upon twice m. In bracket we take first A1 plus A2 common for this multiplied, right, and then in next term we take common, that is RT. Okay, so here we have to take plus in bracket A1 plus A2, sorry, A1 minus A2 into RT. Okay, A1 plus A2 1 and A1 minus A2 into RT we take common, right? So in next step we write this equation reduced to, that is x equal to e raised to minus RT upon twice m. Okay, right here twice m, right? Then we put A1 plus A2 as capital A, and we putting A1 plus A2 equal to capital A, and this A1 minus A1 minus A2 as a capital B. Okay, so A1 minus A2 into R, that is equal to capital B. So with this substitution we can write this equation x equal to e raised to minus RT upon twice m in bracket A plus BT. Okay, A plus BT. So this is the equation which gives the resultant motion, where we consider the case, that is r square upon 4m square equal to k by m. Right? Now we have got the equation x equal to e raised to minus RT upon twice m in bracket A plus BT. So this equation contains two constants A and B. So it is the proper solution of the equation this. Okay. Now when we obtain this solution which contains the two constants A and B, so this is the proper solution, and in this situation the oscillator perform oscillatory motion. That means oscillator perform the motion in which it comes to equilibrium position immediately, right? So from this equation we can say that oscillator comes immediately to its equilibrium position without undergoing oscillatory motion. Okay, so you remember this equation in which oscillator comes to the equilibrium position immediately without undergoing oscillatory motion. Now when we plot the graph of displacement versus time like this, time and here is displacement, then oscillator comes to the rest position without undergoing oscillatory motion. So such type of motion is called as the critically damped motion. Critically damped motion. Okay, so this is the critically damped motion. Now in first case we have got the overdamped motion, in second case we have got the critically damped motion. Now next we consider third case, and in that third case we have to consider case third. In this case we consider damping force is less than restoring force. So consider damping force is less than restoring force. Okay, is less than restoring force. That means we have to write here this r square upon 4m square is less than k by m, or r square less than 4mk. Right? When we consider this case in which r square upon 4m square is less than k by m, then the term that is minus r upon twice m plus root r square upon 4m square minus k by m becomes, that means here this is less than this, right? So this term will get imaginary. That means right here minus r upon twice m plus root r square upon 4m square minus k by m will get imaginary. Okay, so now here we write this imaginary means we will get negative term, and for that negative term we write this minus r upon twice m plus, or we only write this term, right? That is r square upon 4m square minus k by m equal to say I square. Right? I square means we have to write this k by m minus r square upon 4m square with negative sign. Right? So I will write this term, that is root r square, k by m minus r square upon 4m square, and here is I. Okay, because we have changed the sign and negative sign is common here, and that is I square, minus is I square, so we have taken outside the root. So we write here I in root k by m minus r square upon 4m square. Okay, so we write this equal to, or we write this is IP. That means we have to substitute this root k by m minus r square upon 4m square with this I, right? P. Okay, that means root quantity we substitute as a P. Right now, then we write this equation. Therefore, we write x equal to a1 e raised to minus rt upon twice m plus ipt. Okay, we substitute here this term, that is root like this term equal to say ip, right? So we get plus ipt plus a2 e raised to minus rt upon twice m minus ipt. Okay, then we take common e raised to minus rt upon twice m. Therefore x equal to, right here, e raised to minus rt upon twice m common in bracket a1 e raised to ipt plus a2 e raised to minus ipt. Okay, then we use the formula e raised to I theta, and that is cos theta plus I sin theta, and for e raised to minus I theta we write cos theta minus I sin theta. Okay, so here we write this e raised to I theta, that is equal to cos theta plus I sin theta, and e raised to minus I theta equal to cos theta minus I sin theta. So using this we write this term. Okay, therefore x equal to e raised to minus rt upon twice m. Then in bracket we write a1 in bracket, right here cos theta plus, cos ipt, cos pt, okay, cos pt plus I sin pt plus a2 in bracket cos pt minus I sin pt. Okay, like this. So in this equation we take common cos pt and sin pt. Therefore write here x equal to e raised to minus rt upon twice m. In bracket write cos pt common, so a1 plus a2. Okay, a1 plus a2 into cos pt plus I times a1 minus a2 into sin pt. Right? I times a1 minus a2 into sin pt. Then in next step we put this a1 plus a2 some value and this I times a1 minus a2 by some value. Therefore write here substituting a1 plus a2 equal to sin theta. Okay, a1 plus a2 equal to sin theta and I times a1 minus a2 equal to cos theta. Okay, then this equation becomes x equal to e raised to minus rt upon twice m. Okay, and in bracket we write cos pt sin theta, cos pt sin theta plus right here sin pt cos theta. Okay, sin pt cos theta, right? Then lastly we write this is the expansion of sin of pt plus theta. Okay, therefore x equal to e raised to minus rt upon twice m sin of pt plus theta. So this is the last equation. Okay, so if we consider this equation x equal to e raised to minus rt upon twice m sin of pt plus theta. Okay, sorry, here we have to write one mistake is here. When we put a1 plus a2 equal to sin theta, that means we have to put here a sin theta, and here is a cos theta. Okay, so we write here a common and then cos pt sin theta plus sin pt cos theta. So lastly we have to write a e raised to minus rt upon twice m sin of pt plus theta. Okay, so this is the last equation and this equation is the equation of motion of oscillator which performs oscillatory motion. Okay, so this is the equation of oscillator which performs oscillatory motion. Here a e raised to minus rt upon twice m is the amplitude of the motion. Okay, and here is exponential part, that means e raised to minus rt upon twice m. So this exponential part denotes that amplitude continuously decreases with increase in time, but oscillator performs oscillatory motion, right? Now next we consider where we plot the graph of displacement versus time. So when we plot the graph of displacement versus time like this, here is time and here is displacement, right? Then oscillator performs oscillatory motion like this. This is the oscillatory motion where here is amplitude, that is a e raised to minus rt upon twice m. Here amplitude continuously decreases as time increases. Okay, so this equation gives the oscillatory motion, damped oscillatory motion of the oscillator. Okay, now next we consider the frequency of damping. Now the frequency of damping is given by nu d equal to damping frequency, nu d equal to P upon 2 pi. Okay, what is the value of P? The value of P is right here, P equal to root K by M minus R square upon 4 M square. Okay, so this is the value of P. Then we write nu d equal to 1 upon 2 pi root K by M minus R square upon 4 M square. This is the frequency of damped oscillator. Okay, then we write the frequency of undamped oscillator, that is nu equal to omega upon 2 pi. Okay, so what is the value of omega? That is root K by M. So this is equal to 1 upon 2 pi root K upon M. When we compare these two frequencies, by comparing, what we say, the frequency of damped oscillator is less than the frequency of undamped oscillator. That means here we write this nu d is less than nu. Nu d is less than nu. Okay, so from this we conclude that here the damping frequency decreases. That means there is a fall in frequency and decrease in amplitude. These are the two effects of damping. Okay, so when we consider damped oscillatory motion, then there are two effects of damping on that oscillator. The first effect is that there is decrease in amplitude, and second is there is fall in amplitude. There is fall in frequency. So these are the two effects. First effect is decrease of amplitude, and second effect is fall of frequency. Fall of frequency are the two effects of damping on that oscillator. Okay, so with this lecture I stop here. Thanks to all.